Hello everyone. In the previous session, we studied about general feedback structure. So now in this session, we'll study about some negative properties of feedback. And to list out the negative properties of feedback are desensitization of gain, reduction of nonlinear distortion, and reduction of the effect of noise. And with the help of negative feedback, we are also able to control the input and output resistances to the desired value, and it is also possible to extend the bandwidth of the amplifier with the help of the negative feedback. And in the previous session we also came to know that positive and negative feedback are also known as regenerative and degenerative feedback. So now in this session we'll study about gain desensitivity and interference reduction. So this gain desensitivity is all about desensitizing the gain of the amplifier, meaning the gain of the amplifier is made less sensitive to the external factors such as noise. So what we do here is consider the equation of gain of the amplifier with feedback, that is equal to A divided by 1 plus AB, where A is the open loop gain of the amplifier and beta is the feedback gain. So now, in order to desensitize the gain, we assume beta to be constant and we'll differentiate this equation. So we'll get DAF is equal to DA by 1 plus AB whole square, and name this as equation 2. Differentiation of 1 by x is equal to 1 by x square. Remember that formula for this. And now what I do here is I'll divide equation 2 by equation 1. So now upon dividing, what I get is DAF by AF is equal to DA by A into 1 by 1 plus A beta. So D, say let's say x, dx by x is the percentage change in x. That is how we read it. So now here we have daf by af, isn't it? So this is read as percentage change in the gain of the amplifier with feedback is smaller than the percentage gain of the amplifier without feedback by 1 plus A beta factor. So this A beta factor is also known as desensitizing factor. So now we understood from this equation that the gain or the percentage change in the gain of the amplifier is very less when compared to the percentage change in the gain of the amplifier without feedback by 1 plus AB times. So whenever we have feedback, the change in the gain due to the external factors is less by a factor known as desensitivity factor. Remember this, 1 plus A beta is called desensitivity factor. So this is the main advantage of the negative feedback. So whenever we have negative feedback, the percentage change of the gain is reduced when compared to that of the system where we don't have negative feedback. Okay, and next we'll study about interference reduction. What is interference? Interference meaning something that will interfere with the performance of the system, which will abrupt the good performance of the system. So this is mainly decided by a ratio called signal to noise ratio. So if interference is reduced, the signal to noise ratio will be increased. Signal to noise ratio is signal divided by noise. Obviously, if noise is reduced, signal will be increased. Signal to noise ratio will be increased, isn't it? So here, how we will reduce the effect of noise with the help of the negative feedback, we'll study it here. So consider a system wherein we have amplifier A1 alone, and to this we are giving the input signal Vs, and the output signal that we'll obtain from this is V0. Let's say some noise Vn will interfere with this system. So now the signal to noise ratio of this system is input signal Vs by the noise or the interference Vn. For this system, this is the SNR. So name this as equation 1. Now let's consider the second diagram. That is, now we want to increase this SNR or decrease the interference of noise with this system. So what we do is we place a preceding amplifier A2, which is less noisy when compared to that of A1. Alright, so preceding amplifier, meaning before this, we are going, before this amplifier A1, we'll place an amplifier A2, which is less noisy when compared to the amplifier A1. So now the circuit diagram will get modified like this. Okay, here noise is introduced to A1 amplifier, and this is the output. Part of the output is fed back to input with through the feedback network with the gain beta, and this is the input signal Vs. So here whatever the signal is present is beta times the output voltage, that is beta into V0. Okay, now for this system we'll sorry for this system we'll write the equation of output voltage. We cannot write it directly because there are two input signals that we are giving to this system, isn't it? What are they? Vs and Vn. So by the concept of superposition theorem, what we do is first we'll consider only one noise and we'll neglect the other, and we'll calculate the output voltage. Next we'll consider the signal that we neglected in the first case, and we'll neglect the signal that we considered in the first case, and then we'll calculate the output voltage due to that signal. Okay, and then we'll add both the output voltages in order to get the output voltage of this system. Let's see how we have done it. First, say I'll consider Vs alone and V0 I'll not consider. So this circuit will get modified as shown. See here, Vn is not present, meaning interference is not present here. So the output voltage of this circuitry is Vs into the gain of the amplifiers. These are in series, so it will be A1 into A2 divided by 1 plus gain into the feedback gain, isn't it? So 1 plus gain here is A1 into A2, okay, into the feedback gain is beta. So this is the output voltage of this circuitry. In the next case, what I do is I will consider the interference here, and the input signal Vs is neglected here. So the output voltage will be equal to Vn into the gain of the amplifier, that is A1, divided by 1 plus the gain of the amplifier is A1 into the feedback gain. What is the feedback gain here? See here in feedback path we have this feedback network and also this amplifier A2. So the gain of the feedback path is beta into A2. So in the denominator we'll have 1 plus A1 into feedback gain, means A2 into beta. So it will be Vn into A1 divided by 1 plus A1 A2 by beta. Alright. So the output voltage when Vs is considered, when Vs alone is considered, let me term it as V01. And the output voltage when V1 alone is considered, let me term it as V02. Now, what I need here from this analysis is the signal to noise ratio, meaning Vs by Vn, isn't it? So now I'll divide V01 by V02. So let's see what we'll get. V01 divided by V02. Denominator will get cancelled, this even also will get cancelled, and the remaining is Vs by Vn into A2. The signal to noise ratio is equal to Vs by Vn into A2. Previously, the signal to noise ratio was Vs by Vn, isn't it? For a good operating system, signal to noise ratio must be high. Keep this in mind, and now let's analyze. See here, I mentioned this earlier also, but I repeated it for you to recap. So here, signal to noise ratio is equal to Vs by Vn. That's all. By introduction of noise and negative feedback, observe what we got. The signal to noise ratio, Vs by Vn into A2, isn't it? So this is equation 1, which we got previously. Now we got this much. Previously we got Vs by Vn alone. Now Vs by Vn into A2, meaning the gain has the signal to noise ratio is A2 times higher when noise is introduced and negative feedback is present. So even though noise is produced, with the help of negative feedback, we can patch up the effect of noise over the effect of signal. Okay, so this is the concept of signal to noise ratio and the negative feedback. In the next session, we'll study some more properties of negative feedback.